Welcome to Lecture 6. Today we're going to talk about advanced composition. Advanced composition is a celebrated result initially proven by Dwork, Rothblum, and Vadan in a paper in 2010. So today's presentation is very heavily based off some lecture notes of Adam Smith. I'll link these in my own lecture notes for accreditation. His presentation is based off a result of Kairouz, O, and Vishwanath, and also the book by Dwork and Roth. Okay, so today we're going to talk about advanced composition. Like I said, advanced composition is, as compared to basic composition, a much more advanced theorem. In the sense, it's more powerful. So here's the statement here. Let's go through this and see if we can understand what it means. So it says, for all epsilon, delta, delta prime greater than 0, we're going to let M be a sequence of epsilon delta differentially private algorithms. So there's K differentially private algorithms which are run on the same data set. And these MIs are going to be potentially chosen sequentially and adaptively, meaning, M2 can depend on the result of M1, M3 can depend on M2 and M1, and so on. So if you run a whole bunch of differentially private algorithms on the same data set, then you have that the overall result will be epsilon tilde, delta tilde differentially private, where epsilon tilde and delta tilde are these funny parameters here. All right, let's try to read this and comment on this. So first of all, one thing I'll highlight is the fact that kind of the leading term is going to be this one here. This is going to be roughly, if you look at it, if you squint at it, this is roughly epsilon times square root k. It's very crude, but the point is that this is in comparison to if we were just doing basic composition, we would have epsilon times k. So this shows that you can do quadratically better when it comes to the cost of doing k analyses on the same data set than the naive approach would give you. So this is very important to this factor of square root k when you're doing many analyses and in practice. Okay, so this is basic composition here versus advanced composition, this epsilon square root k. Let's comment on some of the other things we have here. So you see here we have this epsilon times k times this funny term here. What should we think about this as? Well, this is roughly, okay, let's pretend we're in the case where epsilon is small. This is approximately equal to k times epsilon squared, very, very roughly. So in the regime where epsilon is rather small, if it's very small, then this will be kind of a lower order term compared to this one. This is what you should generally think of as the dominating term, though in some regimes, of course, it's not the case. And the final comment to make on this definition is the delta prime here. So notice that we have this delta prime here and this delta prime here. It shows up in two places simultaneously. So you can think of it's sort of a trade-off between how big we want the epsilon tilde to be versus the delta tilde to be. So if we choose delta prime to be large, then we have a smaller multiplicative, something smaller multiplying epsilon. This will shrink. But on the other hand, if we choose delta prime to be like small, say close to 0, then the epsilon tilde will increase. So therefore, it's kind of like a balance between the two terms. But generally, you can think of this really the important thing here is the fact this epsilon times square root k. That's the sort of key term here. Okay, so like I said, this is the result due to Dwork, Rothblum, and Vadan. I'll mention that there has been some refinements of this as well. This is kind of like something like this is the best you can hope for, in the sense that there's nothing better than, you're not going to get something like epsilon times k to the 1/3, for example. Yeah, this is kind of the limit. And in fact, it's been pushed to the limit in a result by Kairouz, O, and Vishwanath from 2015. They provide an optimal composition theorem for differential privacy. In particular, kind of this focuses on the case where all the epsilons and deltas are equal to the same value, but you can also imagine that you can handle more general cases where they may not necessarily be the same. and they get optimal answers, which give you these horrible and kind of ugly looking expressions, which can be advantageous in some settings. Whereas this is sort of like a slightly cruder but good general purpose bound. Cool. So before we move on to how we prove this, let's one consequence of this I want to mention is the fact that it allows you to do, let me give you an example of where you can do better before. Remember last time we talked about a simple estimation example where you do the Gaussian mechanism versus the Laplace mechanism. Recall this was estimating essentially, the mean of a set of vectors where, xi is in 0, 1 to the d, and the amount of error that you get, if you run the Gaussian mechanism, then you got error roughly d over epsilon n in L2 norm, whereas the Laplace mechanism would get you error d to the 3 over 2 divided by epsilon n. If you want to test your understanding of this advanced composition theorem, it's possible to show that if you use the Laplace mechanism in the appropriate way, then you can reduce this from d to the 3/2 to the same sort of complexity, d over epsilon n, maybe with some log factors, but roughly the same type of accuracy. And yeah, so essentially it lets you do better than sort of naively applying the Laplace mechanism. There's no free lunch here in the sense that, there's something you lost here. This was a pure DP guarantee, whereas this is an approx DP guarantee. And this one was also approx DP. So yeah, you can't really just get that for free here. Okay, so now that we have the theorem stated and we kind of see that it can help us in some cases, let's talk about the rest of this class. Today's class is going to focus on the proof of Theorem 1. We're going to do this in 2 steps. The first step is a sort of reduction. Here we have general purpose, algorithms M1 through MK, which could have any sort of range. But what we're going to do is we're going to simplify this a lot. In fact, we're going to simplify it so much that we're essentially looking at a binary range. Each thing outputs either a 0 or a 1, roughly. We'll see how it differs from that. But so yeah, the first case is to reduce from general mechanisms down to mechanisms which just output a 0 or 1. And then the second part will be proving advanced composition, essentially, for these very simple class of mechanisms that we're going to reduce to. So that's a 2-step process for today's lecture. So let's start with the first step, where we are going to reduce to binary-ish mechanisms. And we'll see what I mean by that. And we're trying to understand, the following kind of question. What is the simplest pair of random variables which satisfy epsilon delta-esque guarantees? By that I mean, like, differential privacy is a property of algorithms, not of random variables. But I'm trying to say that what is the simplest pair of random variables that satisfy the sort of closeness guarantee that is afforded to the random variables m on x and m on x prime. So let's sort of be a bit more precise here. So we want to know u and v, where these are random variables, and we want them to be somehow simple. And we'll see in a little bit how exactly it's simple, and you'll probably agree that it fits, a natural definition of simple. But we want u and v to be random variables where we have the following bound on their probability loss random variable. So we want the loss between u and v to be bounded by epsilon with probability 1 minus delta. And similarly in the other direction. Now, if you can't remember what the privacy loss random variable is, let's just remind you one more time. It's going to be the following process. Imagine you have 2 random variables like a and b, let's say. So you draw t according to to the random variable a, and then we define that the privacy loss random variable is equal to the natural log of probability that the distribution that you sampled from is equal to t, and divide by the probability that the other random variable is equal to t. So that's the privacy loss random variable, which is kind of going to be big if the outcome was more likely to come from A, and it's going to be smaller if the outcome was more likely to come from B. Okay, so like I said, we're going to want the sort of simplest random variable that satisfies these sorts of things, these two conditions here. And let's see exactly what that type of, what random variable that would be is. And we're going to try to make it as simple as we can. Like, we'd ideally like to make it binary, but you'll see shortly why that can't be. So let's try starting with a binary random variable and say probability that u is equal to t compared to the probability that v is equal to t. Okay, and we're going to define it like follows. We're going to try to do it, define it to have, you know, a natural epsilon delta dp guarantee. So we're going to define it like follows in a potentially arcane way for now. So this is how we define the probability given to symbol 0, where you can see that u enjoys a sort of multiplicatively e to the epsilon probability more. So it'll be kind of tight for one of these constraints. And then we define it symmetrically for 0. Yeah, it'll be, you know, just as you can see, totally symmetric here. On the other hand, you want to also, the thing is, this is of course not a complete probability distribution in the sense that, well, you might notice if you sum this up that then this only sums to 1 minus delta, and similarly this only sums to 1 minus delta. So you need kind of another symbol in order to complete the probability distribution and also handle the case where it might exceed this value. And we're going to want an outcome which literally screams I am u. So in this case, we're going to set this to happen with probability delta. And then v never takes that value, obviously, based on the name. And symmetrically, we're going to have another outcome I am v, which is 0 and delta. Okay, so take a look at this. Hopefully you can convince yourself just by by eyeballing it. Maybe you need to write it down as well, that this satisfies both these constraints, and it's kind of tight in the sense that you can see that it is sort of going to take, it's going to be unbound with exactly probability delta, and it'll take value epsilon in every other case. Okay, so this is the random, this is the random variable that we're going to be considering. And the claim is that this class, or this pair of random variables is kind of expressive enough to express any sort of random variables with this type of bounded privacy loss. So what do we mean by that? Well, this is a theorem which we're not going to prove today, but I'll state it and we'll try to interpret it, and I'll give you a hint as to how it's proved. But okay, the claim is the following. Let A and B be any random variables with you know, bounded privacy loss in both or the same type of privacy loss random variable that we consider between the two. And say that's bounded in both directions. The absolute value is bounded above by epsilon with probability 1 minus delta. Then there exists a randomized mapping f such that this mapping, when applied to u, will be a sample from A and a sample from V fed into this this function will give you B. So what does this say? This says that imagine we wanted to really sample from A and B and compare them. Well, another way to sample from those random variables would be instead to just sample from these much simpler random variables, U and V, and then we feed it into this function. It'll, if it's from U, it'll map it to the distribution A, and if it's from V, then it'll map it to the distribution B. So that's kind of an alternative way of sampling from the two. And this'll be much simpler to deal with, because then we'll only have to reason about, these binary outcomes, or these binary-ish random variables, like I said. Okay, so like I said, we're not going to prove this here. I'll maybe show you a picture on roughly how it follows. Imagine this is the domain, and we have two distributions. So one distribution looks something like, I don't know, say something like this, and like this. So this is one distribution. Let's call this one, I don't know, let's call it A. And then we have another distribution, which is something like this here, and then here. And this is distribution B. So now, how would we, prove this theorem? Well, what would this function do? This function would kind of map the different outcomes to the different ranges of this, to different subsets of the domain here. For example, if you want f of u to really be, we can kind of partition this into 4 different sets. So this is the case where, there's a, probability of, the PDF of B is much greater than, of X. This is kind of much greater than the PDF of A assigned to X. And by that, I mean it's greater than like e to the epsilon times that. So what we can do is, if we sample if we have a sample, what we can do is, if it outputs IMU, then, if it outputs IMV here, then it would map to this subset of the domain where it's like unbounded here. And conversely, you can imagine the IMU would go here, where, it indicates that A is much more likely than B. That goes to this subset of the domain. And for the other hand, for the other ones, like, it's a little bit, you have to be a bit more careful. So how do we define this? We said that U, or 0 is the one that indicates that U is more likely. So you take a look at where the subset of the domain that A is more likely. So for example, here and here. In these cases, roughly, you would say 0 would map to these 2 places. And similarly, on the other hand, 1 would map to the other 2 places, where it indicates that B is more likely. Now, this isn't like a formal proof or anything. This is just kind of an idea. You have to be a bit more careful. It's not going to be a truly like uniform mapping to these subsets of the domain. It's going to somehow depend on the distributions of A and B. But hopefully this should give you an idea of the correspondence, where we say, like, roughly that, we're going to divide it into 4 segments, depending on if the privacy loss random variable would be bounded in those regions or not, and then which one is going to be greater. So that's the idea of a proof, saying that you only need to sample from these distributions in order to sample from the final distributions, from the distributions you really care about. And with this reduction in place, then it suffices to examine the behavior in terms of privacy of U versus V, as opposed to A and B, because of the fact that, we have this post-processing guarantee for privacy, so it'll be sufficient just to look at the things which we fed into this function f. Cool. So that's how we reason about it for just a single pair of random variables. But this doesn't tell us anything yet about differentially private algorithms or anything like that. So let's see how we apply this type of theorem and reduce it to this sort of simple case. And let's be a little bit more precise about some of the things we've defined so far. So the first thing we're going to do is recall that our algorithms are M1 through MK, and these are going to have domain, it's not going to matter much, but this is going to say domain X, the N to Y, say Y in all cases. This is actually a little bit imprecise in the sense that, like, let me take this back in the sense this is actually going to take to be a bit more I'll leave it like this, but the point is we're going to take in a bit more for each algorithm mj. So if mj is the jth computation in the sequence, it's going to take in x, which is going to be the data set, of course, but it's also going to take in sort of a transcript of all the previous things, a1 through j minus 1. Why is this? Like, this isn't an explicit argument to the function, but really, remember I said a key part of the theorem that we're trying to prove is that where they're chosen sequentially and adaptively. So how do you describe the way that mj is chosen adaptively? Well, the way you describe it is basically by looking at the transcript, the results of all the previous algorithms. So really, you could write this as, you know, one way to express this would be like m1 on x, comma m2 on x, where this in turn depends on, you know, m1 on x, the realization of it, and so on. The point is, this is the history of everything else that you saw up to this point, and it's kind of going to be a hidden argument, which we're not going to sort of include it here, but it kind of implicitly takes it. Okay, so what do I want to say? I also want to say that each let me just say that this is going to be epsilon delta dp for any. It's going to have this property for all a1 through j minus 1. So whatever the previous transcript of things we saw is, then the resulting algorithm is still going to be differentially private. And as usual, we're going to have x and x prime be neighboring data sets. Okay, so what we're going to do is we are going to, I'm only going to define, say this sort of a little bit informally, I guess. I'm not going to sort of write this all completely mathematically, but the idea is going to be the following. We're going to essentially just apply this theorem here to each algorithm sequentially. So the idea is as follows. Suppose we have a sequence, z1 through zk, which are sampled from either u or, you know, they're sampled from one or the other. And all we do is for like each j from 1 to k, we're going to apply theorem 2. So what do I want to say? Like, let's try to do this one by one. So what we'll do is say that we'll first have some function f1. So what we have is there's some function f1 first of all, and this is how do we define f1? This is defined so it has the following property. We have it such that if we have f1 on it said this, yeah, f1 on u, that will give us a sample from m1 on x, and similarly f1 will be on v sample from m1 on x prime. So I guess since I actually set up this notation, let me actually use it. Let me rewrite this a little bit. I guess actually no, that was the right way to write it, in the sense that if you know, it actually takes in a sample from these distributions, that'll be where it comes from. So you can see that we've essentially reduced the first mechanism from you know, looking at the general case to just basically sampling based on either u or v. Now, how is f2 defined? Well, f2 is defined in the same sort of way, except the difference is that f2 will sort of implicitly, or I guess explicitly even, it'll also take this sort of hidden argument, the sort of result of the first thing, so a1 through 1, and it'll map to m2 on x, which again similarly takes in this hidden argument a1, 1. And similarly, F2 on V will be similarly M2 on X prime, where it has the hidden transcript A11. But what am I trying to get at here? I'm trying to say that even for the one case, like we kind of already saw that, you know, if we just want to sample from, we want to sample from either M1 of X versus M1 on X prime, we already saw we can reduce it to U and V. All we're saying is that we can do the same type of thing for the second one as well, but this time we have to define the function where it also takes in, the random mapping also has to take in this transcript of everything we've seen so far. And we just keep on doing that again and again all the way to the end. So what's the point of this? What I'm trying to say is that eventually we're going to get some function f star, which is sort of the defined in terms of all these functions, f1, f2, all the way up to fk. I'll just write it like this. And in the end, it'll lead us to this type of theorem. The theorem is the following. It says there exists a random mapping f star such that the algorithm M defined by the composition of M1 through Mk has the following two properties. One is that, I guess I wrote this, sorry, I missed a few things here, but essentially that the distributions are kind of the same, where if you wanted to sample according to M of X, which is where this runs all the different algorithms, then this is going to be sort of the same as applying this function f star that we kind of implicitly constructed here, or explicitly constructed even, on a sequence of random variables drawn according to U, IID. On the other hand, it'll be the same sort of sampling process between if we have M on X prime on the neighboring data set, and we feed V1 through Vk into the same function f star. So essentially, what we've done at this point is reduced it from the general M to the case where we're either looking at a bunch of some function applied to a bunch of samples from U, or the same function applied to a bunch of samples from V. So by the post-processing guarantees of differential privacy, all we have to really look at is trying to understand whether this this sequence of random variables has a low privacy loss compared to this sequence of random variables, and that'll give us correspondingly privacy guarantees for M on X versus X prime. Of course, you know, this f star will be defined, you know, differently for each M and X, and any sort of input you feed into the data set. But the point is, it's kind of like an existential argument, and there exists a way to map it. So all we'll have to do is reason about these, and then it'll sort of apply and carry over the same guarantees as we continue. So okay, at this point, we're done with the reduction. This kind of explains how we reduce from general mechanisms down to binary mechanisms. The next part of the lecture will be focusing on composition of these binary-ish mechanisms, and we'll see how we can get advanced composition for these special restricted cases, which will in fact give us privacy for the overall case.